All right, I'm going to talk to you guys today about the Faraday Lenz law and flux. Uh, so, what the Faraday Lenz law does is it actually says that if a magnetic field through a loop or through a plate or some metal basically changes, it induces a voltage and a current. And this is actually how we generate all of our power in the world. Like power plants work entirely by this method. So you have in power plants you have some method of turning a turbine, which is going to spin a wire inside of a magnetic field. And so in spinning those loops of wire, you actually generate a current, and that current is what we use. And that's why our wall power, when you plug into the wall, has a frequency of 60 hertz, because that's the speed at which it's turning. All right, so let's go ahead and dig into this and how we deal with this. So let's start with flux first. So flux, we're going to use the Greek letter capital Phi. And there's electric flux and magnetic flux. We're going to specifically be talking about magnetic flux today, but they're basically the same thing. So flux is equal to the magnetic field, the dot product of the magnetic field, and the area of the loop. So what this tells me is that if I have a loop of wire and magnetic field passing through it, like this, so the magnetic field passing through my loop, then how big my loop is, in this case it would be the area of the loop, which would be pi r squared times the strength of the magnetic field, give me my flux. So my flux here would be something like b pi r squared in this case. Now, of course, you guys might not realize this, but area is actually a vector. What you need to consider with area for a vector is if I have a length direction this way and a width direction this way, length and width are vectors, right? And so I can't just multiply vectors with regular multiplication. I actually have to do a vector operation, right? So I have two choices. I have dot products and cross products. So cross product is the one you want to use if you actually want to give a non-zero value if they're perpendicular to each other, right? So that means the area of my table, or my area of my page, points out of the page or into the page, depending on what you do. It doesn't really matter in this case. So if I took my loop and had my loop, the same loop, like that, but my magnetic field went this way, all those arrows going that way, then my area vector for my loop is going to point up. That's going to be area, we'll put a B here. So the angle between those two will be here. So it's going to be, so if I want to do it without worrying about areas, which you're going to do most of the time, it's actually going to be a sine, dot product, not sine. I want be a cosine of theta, because the dot product. I want those two to align as much as possible to get the biggest value. We'll say phi. There. Okay, so the only reason we really care about flux is because it's useful in the Faraday Lenz law. And the Faraday Lenz law is the thing that tells us that as we change the flux, we change the current induced and the potential induced in the wire. So let's write that down real quick. So the Faraday Lenz law likes to use the EMF rather than saying voltage. They want to be really specific with what they're doing. So if you're inducing a potential, it is technically the EMF. So it is equal to the number of loops. We'll write this down somewhere below in a second. the number of loops times the derivative, the time derivative of the flux. Like that. So that's Faraday's law, and says that there's a proportionality here. What Lenz did is he came in and actually added this negative sign, and that negative sign is very important. So let me write this down below, what each of these things are. So equals EMF, which you guys should know is electromotive force, but we can just basically call it potential or voltage. It's the same thing. And N equals number of loops. And you guys should know, of course, that, let's put it here, phi is flux. That's what we just did. Okay. So that's the Faraday Lenz law. So, I mean, now that's the calculus version of the Faraday Lenz law. So I know that some people aren't entirely comfortable with that, so we can actually use, whenever you have a derivative, this is what actually appears in your AP formula sheet, is you'll see it more like this. So delta phi over delta t. So the rate of change of the flux, which is the same thing as the derivative. Now, the most basic example you can do with this is to do something like, say, I have a loop. I've got magnetic field passing through the loop, which I've already drawn twice, but I'll do it again. But that magnetic field is decreasing as a function of time. So we'll say it's decreasing by, it's going to be some initial constant value. Let's say 10 Teslas. But it's decreasing by 0.2 Teslas per second. Teslas per second. We'll multiply that by time. So that's going to be my equation for my magnetic field as a function of time. So what is the let's say, what is the magnitude of the potential difference in the current induced? So to know the current induced, I would have to know that this loop of wire, so this is just a wire, it's just a single wire wrapped around, has a resistance of, let's say, I don't know, 2 ohms. I like 2, it's a good, easy number. So we want to solve for what is the EMF, and B, we want to solve for what is the current in the wire. Well, so if I want to look at the rate of change of this guy to get the EMF, right? And I've got this equation here, where I have one loop, so that's just going to be 1. And then what the rate of change of this? Well, this 10 Teslas doesn't change. That's a constant. So the rate of change is just going to be 0.2 per second. So my EMF, and then when I divide by t, that t goes away, right? So my EMF I generate is actually just going to be minus 0.2. Well, I'm sorry, times the area. I didn't write down the area for this. So let's say it has an area of, let's say the radius is 0.1, well, let's say 1 centimeter. So 0.01 meters. So we'll say, let's draw the radius on here. So little r will be our radius, and little r is going to be 0.01 meters. So my EMF is going to be 0.2, because that's the rate of change of the magnetic field times the area. So it's going to be 0.2 times pi times, well, 10 to the negative 2 squared, right? So this is going to be 2 times 10 to the negative 5. So 2 pi times 10 to the negative 5 is going to be my EMF. That's an ugly EMF. All right. So then, and that has units of volts. There, I'll slide that up so you can see it. Now, what is the current? Well, from Ohm's law, we know that voltage is current. Needs to slide this up more so you guys can see again. Voltage is current times resistance, and EMF and voltage are pretty much the same thing. So your current is going to be EMF over R. We said R was 2. So my current is going to be pi times 10 to the negative 5 amps. And that'll be it. All right, I'll see you guys in the next video.